We will add another paper to this flash drought stories. I've actually many drought stories spread out because I record them as the papers or reports come out, and I'm not very good at organizing them. Maybe there can be a drought section, but nonetheless, here we are looking at climate dependent mechanisms which accelerate flash droughts separately in dry lands and humid regions. In the previous podcast, we looked at how humid regions are experiencing increasing number of flash droughts because of precipitation deficits and warming causing vapor pressure deficit, which is driving increasing evapotranspiration and so on. Some people say global greening is also adding to the increasing flash droughts. So flash droughts have drawn increasing attention due to their rapid onset and severe impacts. However, the physical factors controlling onset speed remain poorly understood across climate regimes. This study presents a global assessment of flash drought onset speed using satellite-based evaporative stress estimates and Shapley I don't know how it's pronounced, sorry. Shapley additive explanation interpretation to identify dominant hydrometeorological factors that govern drought acceleration. So we are talking about rate of growth of flash droughts or acceleration. Obviously, we call them flash droughts because there is a dependence on the rate at which it sets in terms of soil moisture deficits. We find that while humid regions experience flash droughts more frequently, events in drylands intensify more rapidly. So previous podcast said exactly that we are seeing increasing flash droughts in humid regions, but this paper says drylands on the other hand are seeing more rapid intensification. This contrast reflects differences in energy and water constraints. Net radiation plays a greater role in humid regions, whereas surface drying dominates in drylands. Moreover, short-term antecedent moisture recovery followed by rapid drying accelerates the onset with soil moisture depths and time scales exerting region-specific influences, hence the climate-dependent mechanism or climate regime that determines how the acceleration happens. These results reveal climate-dependent mechanisms underlying flash drought intensification and highlight the need for tailored monitoring strategies in diverse hydroclimatic contexts. So if you're thinking about setting up monitoring networks for growth of flash droughts, then you should be aware of what to look for based on the background climate. So flash droughts can develop within weeks and pose serious risks to agriculture and ecosystems, which is the plain language summary. This study examines how quickly flash droughts form in different climate regions and what influences their rapid onset. We find that flash droughts are more common in humid areas but intensify faster in dry lands. In humid regions, energy from net radiation speeds up drought development, while in dry lands, drying of the land surface and soil moisture loss are more important. Surprisingly, short-term moisture recovery before a drought can actually accelerate its onset. So there is a recovery. There's a verb missing there. These findings improve our understanding of flash drought mechanisms and highlight the need for region-specific monitoring strategies. I will skip all the text and just go through a few figures and read just one bit of the discussion and conclusion. We're looking at mean onset speed in percentiles. So you are looking here at arid, semi-arid, subhumid, and humid climates, and you can see the box and whisker plot. We'll also see a violin plot in a minute, but you can see the distributions. You can look at fast developing categories here: FD1, FD2, FD3, and FD4. So global flash drought frequency and onset speeds are shown. Global distribution of mean onset speed indicated by the average SESR decline during the intensification phase of flash droughts from 1980 to 2022, and global distribution of frequency represented as the percentage of years affected by flash droughts from 1980 to 2022. Okay, so somebody is knocking at my door here. Give me 1 second. We'll be back in a second. my stop. Sorry about that. So my computer, my mouse is kind of acting funny. It's lost its sensitivity, so even when I keep banging it, it doesn't respond. Anyway, we were discussing the flash drought frequency and onset speeds. We are looking at mean onset speed in percentiles here for the categories of flash droughts, and here percentage of years with a flash drought. So frequency again, arid, semi-arid, subhumid, and humid. I think I said everything, but yeah, okay. SCSR is standard evaporative stress ratio, which is the actual evaporation divided by potential evaporation. So atmosphere has certain demand for moisture, but moisture may not be available, or evaporation may not be meeting the levels of potential evaporation. So that ratio is ESR, so SCSR is standardized. So you are looking here, let's read the caption first. Flash drought frequency across onset speed categories, global distribution of flash drought frequency intensification categories, moderate FD1, severe FD2, extreme FD3, and exceptional, so FD4. Moderate, severe, extreme, and exceptional. Red and blue outlines delineate regions where over 50% of the events exhibit extreme and exceptional onset speeds, and over 80% are moderate events respectively. Distribution of flash floods is shown in figure B. We'll go back. So this one, let's look at this and then go back. Distribution of flash floods, drought frequency within climate regimes again. So remember the speeds here with moderate, severe, extreme, and exceptional. Okay, so these are the violin plots, and you can see events. So you have box and whisker, but you see additional information in terms of the standard deviations. So distribution of variances are also visible in these, and you can see semi-arid is going from FD 1 to FD4, so you drop the percentage of events here in semi-arid. Subhumid again drops this way, whereas humid is somewhat higher in FD1, but almost equal in others as well. So you can go back and read more carefully what happens, but we'll look at the mechanisms in a minute. Red and blue outlines delineate regions where over 50% of the events, as we said. Distribution of flash drought frequency within climate regimes from arid, semi-arid to subhumid and humid for each onset speed category. For each grid cell, the percentage of events across FD1 to FD4 sum to 100%. The box plots show the distribution of these grid cell level percentages across all the years for 1980 to 2022 within each climate regime. Of course, all frequency differences across onset speed classes within each climate regime and across regimes for the same class are significant at the 9% level. So you have to make sure you are classifying them based on statistically significant differences. The climate regimes are of course different, but nonetheless you can see here percentage of events. The colors you have to remember from here. Subhumid and humid have these bluish colors, dark and light, and arid and semi-arid have these magenta-ish colors, dark and light. So you have arid, semi-arid, and humid, subhumid. Okay, so take those for what they are. We'll just look at the numbers and mechanisms. So you can see the categories are moderate, severe, extreme, and exceptional. Okay, so maybe you can read the details yourselves. I'm being very brief here. So we are looking again at E and potential E so that you can look at evaporative stress ratio, contributions of E and potential evaporation EP to flash drought onset speed. Global distribution of E and EP mean contributions here for each one of them. So you have to map each one this way. And this is E contribution, EP contribution, and contributions in percentages for each region averaged globally. So arid, semi-arid, subhumid, and humid. E and EP contributions within climate regimes, so that's B. And am I missing something here? This is B, sorry. This is A, evaporation, potential evaporation, E and EP contributions within the climate, each climate regime for each onset speed. So we are looking at FD1, 2, 3, 4 in arid, semi-arid, subhumid, and humid. So many details, but you can track yourselves the details. But this is probably the best way to summarize it. We are looking at flash droughts in arid, semi-arid, subhumid, and humid regions, climate regimes, and we are looking at changes of E during rapid intensification phase, E plus and E minus. So you can see changes of E and EP during rapid intensification here for arid and semi-arid basically shows E plus and EP plus, so both potential evaporation and evaporation are going up. And similarly, I mean, they are for all categories, but you can see that for some categories, evaporation is decreasing, but potential evaporation is actually going up. And you have to understand that evaporation is what actually happens, and that obviously depends on availability of water vapor, soil moisture, winds. So there is a nonlinear relation between temperatures and evaporation, but the wind dependence is linear. So similarly, you have semi-arid for FD1 to 4. So you have both increasing in some cases and only one increasing. Here both are actually decreasing, E minus, EP minus, but you can get, that's where you can get moderate flash droughts. Okay, so here evaporations are increasing. You can see how they map onto changes in E and UP during rapid intensification. I won't say much, but you can see all kinds of processes happening in each regime. These are hydrometeorological drivers. So NR, oops, I'm not remembering all the how do I do this? Let me open the file over here and make sure we get the acronyms correct, which I should have done already. El Nino, Flash, Flash droughts, dryland and humid. I cannot search here. I have to open it. Sorry about doing this in real time, but let me pause it and do it. I should have written it down. I always read the paper, think I'll remember, but then I forget. Okay, sorry about that. Maybe it should have been intuitive, but it's not. So that's net radiation on setup. So we will see soon that as we saw in the abstract, net radiation can be a driver in some climate regimes, and there are other factors we see here. SM soil moisture, surface soil moisture is SM surf, of course, right? Surface soil moisture, SM surf, onset down. VPD is vapor pressure deficit, and atmospheric temperature. So root soil moisture can be surface or root depths, obviously, and there are lags. So you can see lag 5 days, 30 days. You can see that the boxes get small. Sorry about that. My computer tried to crash, so hopefully it's just a brief interruption. So obviously you can see that there are all the processes playing a role, but some are dominant. So you can see thicker lines. These network diagrams have lots of information in them, but you have to understand. So there are some very thin lines, some lines are thick and thicker. So you can see how they add up when you come to this radiation effect, soil moisture, surface soil moisture effect, vapor pressure effect, atmospheric temperature. They're all related. Warmer atmospheric temperature will increase VPD, which will increase evaporation, and potential evaporation depends on other factors, and root soil moisture. So that can depend on the persistence timescales, but we are only looking at the onset rates. So you have to see the climate regime dependent onset rates depend on all these factors. Of course, precipitation anomalies also, and they play with 5-day lag periods here, going back to humid periods. As we said in the previous podcast, humid regions are seeing more flash droughts, whereas here idea is that drylands are also seeing flash droughts, but more intense, more rapidly intensifying. Okay, so collectively our findings suggest that flash drought onset speed is governed by distinct hydrometeorological controls across climate regimes, shaped by the interplay between the atmospheric demand for water vapor, VPD for example, and soil water availability at different depths and timescales, so surface and root depths and with lags. While humid regions are more prone to flash drought occurrence, as we saw in the last podcast, dryland events tend to develop more abruptly, associated with shallow soil moisture depletion and enhanced atmospheric coupling. Understanding the spatial patterns and dominant predictors of onset speed not only advances insight into the mechanisms of drought intensification, but also offers useful predictors to enhance forecasting skill, ultimately supporting early warning systems and strengthening the resilience of agricultural and ecological systems to flash droughts. But of course, monitoring systems also can take these sorts of details into account so that you are monitoring for the right things in the right climate regime. Okay, so let's leave it here.